So if you've got a situation where the mechanical energy, and remember that is the kinetic energy plus the potential energy, is conserved. That is, there are no outside forces doing work, or at least when you add up all the outside forces doing work, the sum total is 0. Then you can make a potential energy diagram, which can be super useful and tell you a lot about what's going on. So let's do an example where we look at gravity. So you've got your diagram, which is energy versus position. Remember, potential energy is the energy you've got due to where you are, the energy due to your position. So if we go ahead and do this, and let's do potential energy in purple. And so the potential energy due to gravity is mgy, where y is your height, and then plus some constant, which depends on where you put 0, but of course usually we ignore that and just put 0 right here at position 0. So if we graph this potential energy, it's going to be a line like this. And the position is going to be the height, which is equal to y. And well, right off the bat, there are a couple things we can tell. So the potential energy is going to be, dependent on position. In this case, you multiply mg times the position. So the slope is mg here for the potential energy. And remember that the change in potential is given by the negative of the integral of the force dotted with this little position that you're doing the integral over here. And that means if you take the integral of the force to get the potential energy, then to get the force back, you'll undo that by taking the derivative of the potential. And if you take the x derivative, that'll give you the x component. So the force is going to be negative the slope. The slope's mg, the force due to gravity is negative mg, where negative says, okay, if we're making this going higher, the force is opposite that direction. So that makes sense. The force is always going to be down, pushing you down towards like the ground or whatever is at 0 here. Now let's make the total energy E. Just give it some value. So it'll be constant. That's what conserved means. It means the total number, when you add the kinetic and the potential energy, it's equal to some constant. So that is our constant energy. And it's just a straight line. It doesn't change with the position. Potential's changing, but the total energy isn't. And that means that if you're at some position, say this one, you're going to have this much potential energy. And the rest of it's got to be kinetic energy to make up the difference, because potential plus kinetic, that's the total energy. So let's just write that down. In orange K, we got kinetic energy, which is your energy due to your motion, which is 1/2 your mass times your speed squared. So if we move up this way, we're going to have more potential. So U will get bigger. K will get smaller. If we move this way, we're going to have more kinetic because we got less potential. So that's one thing you can get from the potential energy. You can just sort of look at any position and say, all right, how much of my total energy, this red line up here, is potential energy and how much is kinetic energy? So more potential as you go to bigger y's, to higher heights, makes sense. More potential, less kinetic. So if this is the ground, say what's happening is we are throwing something upwards. It's slowing down, slowing down, slowing down, gaining potential energy. It gets higher and higher until we get to this point right here. So that point which is where the potential energy equals the total energy. So we don't have any kinetic energy, it's equal to 0. That guy is a turning point. So you can always mathematically tell that you've got a turning point when you set the potential energy equal to 0. That will tell you at what position you were getting this turning point. And it's called a turning point because, again, think of this as we've got an object, it's in gravity. The position is the height, so as it goes up higher and higher, it's losing speed, it's gaining potential energy, losing speed, gaining potential energy, until eventually it gains so much potential energy that it's got none left for kinetics, so it stops. And what does it do then? Well, of course, it turns around and goes back down the other way, because when you are throwing objects upward, when that direction is y and this direction is time, they travel upward and then they stop and they turn around. So that's what's going on, except for going up and down like this. The traveling's happening like this. It goes up, it slows down, it stops, it turns around and falls back down that way. So this is how you can use a potential energy graph. It tells you some other things. It also tells you, going to go erase some of this so I can have a little more space to write. All right, so got a little more space. It's also going to tell you that everything sort of beyond this position, all of this stuff is forbidden because your potential energy is bigger than your total energy. And if that's the case, in order to make this guy true, that your total energy is equal to your kinetic plus your potential, if your potential is bigger than your total energy, that would mean your kinetic energy would have to be negative. And that doesn't make any sense given what's going on here. Your mass, physically, that shouldn't be negative. The square of your speed, that shouldn't be negative either. So this is forbidden. You can't go here. And that, again, makes sense when you think of like throwing a ball up. It travels upward, it stops and slows and turns around when it gets to this height. It never goes higher because it just doesn't have the energy to get up here. Can you go down this place? Yeah, you totally can. So we would go to negative potential energies when we're here, but that's completely allowed. That just means you're at height that are below wherever you set the potential energy equal to 0. And maybe if this is the ground, we've dug a hole in the ground, and so the ball can keep falling into that hole, getting more and more and more kinetic energy because its potential energy has gone negative. Makes sense, totally physical. All of this fine. This is not fine. Can't have the potential bigger than the total energy. Okay, let's look at another example, that of a spring. So the potential energy is 1/2 your spring constant times your position squared, that distance from equilibrium. So if we go ahead and graph the potential energy here for a spring, we would get energy on this axis. Make that a little bit taller. We'd get position on this axis. And here position would be x. That, remember, is the distance you stretch the spring from equilibrium. And then graphing this potential, the x is squared, so it would kind of zip up like that. That would be our potential. And of course, x doesn't have to be just positive. It can also be negative. So we get a mirror image over here, but I extend the axis too. So positive x, maybe that means that we are stretching the spring this way. Negative x, maybe that means compression, or vice versa, it doesn't really matter. Again, we're in a situation where the total energy is conserved, so E, the total energy, is going to be just a constant no matter where you are. And we can do the same thing here. We can look and say, okay, where do we have more potential when we move out farther away from the equilibrium length? So here we got a lot of potential, a little bit of kinetic, less potential, more kinetic, almost no potential, lots of kinetic. Here, right in the middle, it's all kinetic, no potential. That's at x equals 0. That is when we're at our equilibrium length. So let's go ahead and write that in. That's when our string isn't stretched at all. Okay, so things that we can find. We got 2 turning points right there. So there's a turning point, there's a turning point. again, as the name suggests, that is where you have your little mass on the spring, starts with equilibrium, you stretch it out here maybe, and you let it go, and the spring will pull back. Right here, it doesn't have any potential energy, but it does have kinetic energy. It's moving backwards, so it keeps moving backwards, stretches, but slows down, hits this turning point, and the spring is compressed as far as it can go, and so it starts moving back to equilibrium, overshoots, stretches, hits this, turns around, comes back, and that's what the spring is doing. It's bouncing back and forth between this point and that point. Again, you've got the forbidden regions beyond the turning point. The spring is never going to move out to see this position, because at this position, the potential energy is higher than the total energy. Same thing over here, kind of everything past this turning point is forbidden, because again, the potential energy is higher than the total energy. Can't have that, because you can't have negative kinetic energy. But now we've got another interesting point, this equilibrium point, when we're at x equals 0, when the spring isn't stretched at all. So right here, what's going on? It's equilibrium length of the spring, meaning it isn't stretched or compressed, but it's also an equilibrium point on the graph. Remember, equilibrium means force is equal to 0. And the force, recall, is negative the derivative of the potential. So looking at the graph, yeah, that's the slope. Force is the slope. And so there the force is 0 because the slope is 0. And in this particular case, this is what is known as a stable equilibrium point. And that just means that the object is going to stick around. So mathematically, if you've gotten this far in calculus, if you have a stable equilibrium, and that just means you're sort of at a minima. It doesn't have to be a, minima for the whole thing. It could just be a little dip in the energy like this. But what that means is if you look at the second derivative and you're trying to figure out this mathematically, that second derivative is going to be positive. If that's the case, you're at a minima, you're at a stable equilibrium, and physically what that means is whatever object is moving this potential will tend to stick around the equilibrium. So we can see that just in having even this much energy here, the spring is going to bounce back and forth around this point. And you give it a little less energy, it'll bounce, kind of back and forth, still around that point, but it'll get closer, and the less energy it's got, the more likely it is to just sit here. So that's one way you can think of equilibrium points. The force is 0. That's our definition for equilibrium, but in terms of potential energy diagram, it's a place where you could just put the object and it would stay there. You could balance it there. And that brings me to another way to think about these potential energy diagrams. You can think of them as like a marble, just moving on a track that's shaped like the potential energy. That'll tell you what the object under this potential is doing. So here, if we put a marble right here and we don't push it, so it doesn't have any kinetic energy, what that marble is going to do is it'll stay here for just a slight moment because it doesn't have any speed, and then it'll start traveling downwards, going lower and lower, picking up kinetic energy, has the most kinetic energy it's got here, and then it'll travel up the track, slowing down till it hits this turning point. That's where it's turned all of its total energy into potential, has no more kinetic energy, can't move, so it turns around. So the marble would be rolling on the track. So then you can think of an equilibrium point as a point where you could balance the marble, and the turning point as a point where the marble on this potential energy track would turn around. You do, of course, you have a stable equilibrium point here, which is a minima. You can have a unstable equilibrium point, which we don't have on this graph, but we could have on a different graph. So an unstable equilibrium is going to be a max. So where the potential energy would do like this. So you'd still have the slope being 0, say right there. That means the force is 0. And we could potentially take our little marble and balance it at the top here, but it moved off just even a little bit, it would go rolling far away. So a stable equilibrium is one where the marble will stay put even if it gets nudged or a breeze comes by and blows it. It'll kind of stay around that area. An unstable equilibrium is one where if you nudge it just a little bit, it'll just roll off, go away, and never come back. So that is one way to think about potential energy diagrams. Just think about them as tracks. You roll little marbles around, that'll tell you what's happening at the turning point. That's where the marble turns around, given how much total energy it got. Equilibrium points, that's where the slope of the track is zero, so the force is zero, or it's a place where you could potentially just stick the marble there and you could balance it, either in a stable equilibrium, a minima like this, or an unstable equilibrium, a maxima like this.